Good afternoon, everybody. Thank you for coming out today to listen to the last formal seminar of our fall seminar series. Just a couple of announcements. The first is next Thursday is the departmental holiday luncheon, so that's around noonish time over in the Good Barn. It looks like we've generated the money for it all, so that's great. And unfortunately, I'm going to be out of town next week, so Todd will be filling in for me as the MC of that. Last we checked, I think we had 90 people RSVP, so it should be a good crowd, and hope to see you guys there. The next announcement is Friday. Next Friday is the IPS Symposium. So our grad students, we have 3 sessions of, I guess, about 4 grad students each that will be having presentations throughout Friday in this room. We'll also have a noontime chili contest, if you haven't seen that being advertised. Right now, we've got 6 contestants who have offered to bring us their best chili. At least one of them is vegetarian and vegan friendly, so if you have dietary restrictions, we should have something that should be able to accommodate you. We'd like to get maybe 3 to 4 more, so if anybody feels like brushing off their chili expertise, let Abby know, and she can get you signed up for that.
Tell people to bring.
Oh yes, and bring cash to vote. So again, I'm not going to be there, but I'm going to seed 3 $50 bills to different people to do voting for me. So you get to vote with cash, and then all cash proceeds go to the Grad Student Association. So come and let your vote be known there. Any other announcements that I'm not remembering? No? Okay. Then it is my pleasure to introduce one of our own today, Jason Unrine. I think almost all of you know Jason. He has been in his current position or a professor here in our department since it looks like 2008, I believe. So about 10 years. Jason is from the Cincinnati area, and I think traces his interest in environmental toxicology and environmental science in general to growing up in kind of a heavily impacted neighborhood, it sounds like, at least from what I've heard you say in the past. And so, as many of you know, old Rust Belt cities with industrial histories have often lingering environmental issues, and it has sounded to me like Jason has been interested in those in part from where he grew up. He got his PhD from the University of Georgia in toxicology, and has been extremely productive, as I think most of you know. I can embarrass him and read all these things. He has more than 5,000 total citations, an H index of 41, blah, 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 blah. Jason is quite successful. And so I asked him to come today and talk about some of this new stuff that I think many of us may not be super aware of what he's doing in sort of a blend of environmental and health-related stuff. Right? Yes, I got that right. The only other thing I would add is that for a brief time, when I was in the board unit, I tried to do a little trivia or coffee social. And we did it as a group. I came with the questions, normally 10, and we see how we fared. And our scores were always better when Jason was there. So, here you go, Jason.
Thanks a lot for that introduction. Can everyone hear me okay? All right. Well, good afternoon, everyone. Thanks for coming out. So you're used to hearing me talk about nanomaterials and agroecosystems and things like that, but I have sort of a whole other research program that goes on in parallel to that you haven't heard much about. So I've been doing work on environmental exposures and human health with a focus on Appalachia. So this is a picture of Red River Gorge. When I was a kid, this was like the first place that I ever really experienced nature. And so it always had an impact on me in terms of being interested in science and things like that. As Rebecca mentioned, I grew up in an area that looked like this. This is actually at the end of my street, what it looked like. So, you know, I was around sort of the decaying remains of some pretty heavy industrial areas as a kid. And so from a pretty young age, I got interested in people's exposure to chemicals and potential health effects and things like that. You can sort of think of my childhood as like an urban version of Stand By Me. So I lived right on these railroad tracks. And, you know, we would throw rocks through windows of old factories, things like that. So really from the age of maybe 12 or 13, I started getting interested in this sort of thing. So what I'm really going to be talking about today is exposure science. So exposure science is really the science that...
Sorry, your microphone fell off.
Oh.
Hanging down. There we go.
So exposure science relates a couple of different things. So the first thing that you're sort of used to hearing about is sources of environmental contaminants, how they move through the environment at different levels of intensity, and how these chemicals, how there's exposure to humans. So management exposure. But there's a whole other aspect to it that gets really complicated, which is what the time, activity, and behavior factor. So what do people do? Where do they do it? How long do they do it? That sort of thing. And those two things sort of interact to determine people's contact with contaminants, the dose that they get, the internal dose, and then eventually how that chemical reaches the ultimate molecular receptor that initiates a toxic response. And then that all determines the outcomes. And then there can be feedback to these things. Boy, this pointer does get really disorienting when you're that sort of feedback to these things. So in the region that I've been focusing on here in Kentucky is the Appalachian region. And it's not the same thing as the Appalachian Mountains, actually. So the Appalachian Mountains extends all the way from Alabama all the way up to Newfoundland. It's a really long mountain chain. And the Appalachian region encompasses really the central and southern part of that, but it's more than that. So you can see from this map that it actually extends quite a distance from the mountains themselves, and it's really a cultural region. I grew up here in Cincinnati. We're here in Lexington. You can see both places are sort of on the fringe. Then Atlanta is right here, which is also on the fringe. So you have like two major metropolises that are sort of on the fringe of Appalachia. And then you have Pittsburgh here, which is the only major metropolis that is sort of completely contained within Appalachia. So in terms of the significance of this region, it contains 25 million people, which is similar to the population of Australia. And the land area is about 530,000 odd square kilometers. So it's roughly the size of Spain. So we're talking about a very significant land area and population here. And if you look at the prevalence of different diseases, the central and southern Appalachian region has pretty high disease prevalence. So this is 2013 diagnosed diabetes prevalence. So you can see, the Ohio, West Virginia, Kentucky part, pretty high. Of course, there are other regions that have pretty high prevalence of diabetes. The coastal plain, Mississippi, and Alabama. So it's not exclusive to Appalachia. But it is one of the higher areas in terms of diabetes. If you look at colorectal cancers, again, focusing in here, one of the highest prevalences in the country. This figure here is actually showing the change from 1980 to 2014 in the prevalence of colorectal cancer. And you can see that in the Northeast and the West Coast and the Great Lakes, it's actually gone down quite a bit. So the incidence of cancers overall has gone down over this time period. But if you look at right on the region of the border of West Virginia and Kentucky, it's actually increased quite a bit, up to 60%. So we have something different going on here than is going on in other parts of the country. So I'm going to focus in on something that's even more specific to Kentucky in our part of the Appalachian region, which is mortality from tracheal bronchus and lung cancer, so basically lung cancer. And you can see southeastern Kentucky has the highest lung cancer rate in the country, pretty much. So you're talking about the lowest incident areas is about 20 or so per 100,000 people, and you can have over 200 per 100,000 people in this part of Kentucky. And it's really pretty specific to this area. And you can see with the same change figure from this mock data owl paper that it's one of the areas where it's increased the most since 1980. even though the smoking rate has kind of gone down a little bit over that time period. I'm actually missing a figure here, but I can just tell you what it says. Basically, you would think that it's like smoking that causes that, but really the smoking rate is high all over the state. It's not that much higher in that part compared to like the Louisville area, which has a much lower incidence rate. I may have that slide a little bit later on. So this is the age-adjusted cancer mortality rate, 1994 to 2015 on a county level. This is from Kentucky Cancer Registry. You can see these counties have a much higher cancer mortality rate than the rest of the state. So Lexington is here, Louisville is here, Northern Kentucky. So there's something specific going on in this region. And the current hypotheses that people discuss in the Cancer Center, that are the epidemiologists that really study these things, are smoking, diet and exercise, genetics, environmental exposures. Those are sort of the four leading hypotheses. So I mentioned smoking, and I may have this on the next slide, right? So this is smoking rate by county, and you can see it's actually pretty high. The nationwide average is like 17%, but Kentucky is 26%, so it's higher than the nationwide average. And you do have some areas that are higher, but you have some areas that are similar than lower than the parts of the state, such as around Louisville, where the lung cancer rate is much lower. One thing that always comes up is the influence of coal mining and whether that might have caused environmental exposures that somehow interact with cigarette smoking to cause lung cancer. So this is a map just showing different regions of Kentucky. So we have the Big Sandy watershed, Kentucky River, Cumberland Valley, and the amount of coal produced in 2013. So these are pretty heavily, historically heavily mined areas. So the hypothesis comes up that there may be contaminants. And one thing that people throw around is that maybe there are metals in the coal, or trace elements that people are exposed to as the coal is mined. So this is some research that we did looking at selenium in coal and overburden from coal. So selenium is a major issue because birds and fish are very sensitive to selenium, and it can cause reproductive problems that cause population level impacts. So if you look at like a core through a coal mine, this is the elevation above sea level. You can see that, so this spike here is the coal seam itself, much higher selenium concentrations than sort of the background overburden. Also, certain types of shales and fire clay. So fire clay is basically fossilized soil. It's often found in association with coal. So if you take these samples of the coal and the black shale, thin section them and look at the distribution of selenium using X-ray fluorescence, you can see here in reflected light these little shiny things that are sort of embedded in the coal. Turns out that these have quite a bit of selenium in them. Here's an overlay here. But the selenium doesn't just occur there in isolation. If you look at the speciation of the selenium, so if we go in and do X-ray diffraction on one of these individual particles, we find out that that's actually lead selenide. So, there are all types of different minerals that were actually precipitated or formed when sediments were laid down during the Carboniferous in these swamps that find their way into the coal. So there are definitely trace elements associated with these deposits that can be liberated. So when I first got involved with this was with a study that Nancy Johnson from the epidemiology department led up. And we opportunistically got some samples that were collected for a different study of toenails that we could use to analyze this trace element exposure, which I'll describe more in detail later. And so we actually compared, this is what's called an ecologic study. So you're just comparing two different regions that have different disease incidences, but you're just looking at controls, more or less. There's no differentiation between cases and controls. And so we have the sample, we have 150 people from Appalachian, Kentucky, or from Jefferson County, 80 from Appalachian, Kentucky. You can see the smoking rates here. It's a little bit higher, but not dramatically higher than in Jefferson County. But if you look at the sort of never smoked there, it's pretty similar. What we found was that if you look at certain concentrations of certain elements in their toenails, so if you look at arsenic, for example, if you compare Jefferson County, so these are just the different percentiles. Jefferson County with Appalachian controls was higher for chromium, nickel, arsenic. One of the problems with this study was that we had a very large number of detection limit observations because the samples were collected by someone else and they were extremely small. You could barely see some of the samples. So we had to use some fairly fancy statistical techniques to compare these. And they're significant, but it still needs further study, and there's no differentiation between case and control here. There was also a study that was done out of UCLA and Dartmouth around the time that I got here in 2009. And actually my postdoc advisor, Brian Jackson, analyzed these samples. So he's the one that I phoned up and said, hey, how do you do this? So we're analyzing them using the exact same methods. And they found that not if you look at all lung cancers, but if you look at certain types, which are the small cell and squamous cell carcinoma. And this is showing odds ratios here, if you're not familiar with that. In these categories, so if I were to increase the exposure of arsenic 1 unit, that's the increase in the odds of having lung cancer, for example. So you can see these are greater than 1, and they're significant for pretty low levels. So then a bunch of people got together, led by Suzanne Arnold, who's a physician here in the Markey Cancer Center who works with lung cancer, to do a larger study here in Kentucky. It was a case control study. So this is a different experimental design where we have matched people with lung cancer and controls. And we focus just on the southeastern portion of Kentucky. So a bunch of people involved in this. So the study design was the Kentucky Cancer Registry. They received the pathology reports for all the confirmed cancer cases in the state. And they contacted people that were diagnosed cytologically with lung cancer. And if they agreed, they were contacted by study personnel to see if they would agree to be part of the study. And then we used random dialing from voter rolls to obtain age and sex matched controls and compare them to. And so nurses from Kentucky Home Place, which is part of the Center for Excellence in Rural Health that's in Hanford, Kentucky, they conducted home visits, and we did a questionnaire that covered smoking, occupational history, diet, exercise, residential history, all that sort of stuff. We collected blood, urine, hair, and toenail samples, drinking water samples, garden soil. We placed radon detectors into the homes. So getting to why do we use toenails as a biomarker of exposure? So if you use something like blood or urine, that's typically reflective of more like 24 to 48 hours of exposure. There's a lot of research, particularly for arsenic, suggesting that toenail is a better biomarker. So as the nail matrix is laid down, it takes about a year or so for the tissue that's being formed to get all the way to the end of the nail. So when you collect nail clippings, you're integrating exposure of a month or two, but it occurred maybe a year or so prior to the actual exposure. So one of the things with arsenic is that there are organoarsenical compounds in seafood, and that's the major source of exposure for people. But these compounds are usually quickly metabolized and excreted in the urine, but they're not really as associated with the nail arsenic. So the nail arsenic really is more reflective of inorganic arsenic exposure, which is what we're concerned with here. And of course, we're looking at other trace elements as well, but on the outset, we knew that there was some evidence that arsenic was associated with lung cancer, so we were looking at that primarily. So this is the demographics of the volunteers for the case control study. So in this experimental design, we obtained good statistical power by having 3 times as many controls as cases. So this is a little bit bigger than the New Hampshire, Vermont study. We had 100 cases, 267 controls. As you can see, because we're talking about lung cancer cases, the median age is 62 years old. We had a statistically significant difference in BMI between the cases and controls. So this is body mass index. And actually the cases tended to have a lower body mass index. And this is probably reflective of the fact that they were sick, by the time we contacted them. We had, we tried to match on gender. When you look at the smoking data here, so we have current, former, and never smokers. I would focus mostly on the never. So you can see in the controls, 51% of the people never smoke. In the cases, 3% of the people never smoke. So you hear stories about, well, so-and-so smoked and they didn't get lung cancer. That happens, but there aren't very many people that get lung cancer that never smoke. So that's the other side of the equation. So I'm just going to jump right into what we found in terms of the trace element concentrations in their nails. And to our surprise, we found that cases and controls had pretty much identical arsenic concentrations, and they were pretty low. So, a lot of sort of hypotheses that people put out there about arsenic exposure in southeastern Kentucky didn't really turn out to be borne out in this study. One thing I want to point out, though, and this is really important, is that this is not a random sampling of all people in eastern Kentucky. This is a sampling of people that had lung cancer and people that were matched based on age and gender to them. So this is just a case control study. This isn't telling you that, no, there's no arsenic exposure out there, but it's telling you that it's not associated with lung cancer. We saw a little bit surprising results with some elements like selenium, manganese, and chromium. So you'll see that cancer cases actually have lower levels of chromium than controls. Manganese levels were lower in cases than controls. And selenium levels, although it's hard to see here because this is the aggregated data, and it depended on whether you were a smoker or not. So you'll see it in the statistics later, it's a little bit lower in cases than controls. So this was like really surprising and not what anybody expected at all. So that's when they let the soil scientists write up the paper. So when you look at the logistic regression results, so we did a univariate logistic regression model that just looked at, so these are odds ratios. If you increase the exposure by 1 unit, the increase in the odds of having lung cancer. You can see that there was a couple that were statistically significant, like chromium, aluminum, manganese, but the odds ratios were less than 1. So that meant if you had higher levels of those elements, that you had a lower probability of having lung cancer. We also did a multivariate model that included age, sex, smoking, body mass index, and the other trace elements. So it adjusts for all those factors. And the only thing that came out significant was manganese. And then nickel came out sort of like marginally significant. So really there was no positive association between trace element exposure and lung cancer, despite kind of the lore on that. So we're in revision with this right now. So, the initial hypothesis, we found no association between arsenic exposure and lung cancer. The exposure levels were low, with median toenail concentrations around 0.05. In the SECAT ALF study, they saw that once you got above that level, that's when you start seeing increased risk of the small cell and squamous cell carcinoma. Now, when you look at arsenic in surface soil, so tying it back into soil science here, so there's definitely an intimate connection between soils and human health. You can see that the Appalachian region of Kentucky doesn't have really that high levels of arsenic in surface soils. In fact, it's really more around Lexington area where you see the highest levels. In Ohio, up here in New Hampshire, these are the areas that have higher levels of arsenic. Although it's nothing like what you would see in places like Bangladesh, where there's like hundreds of parts per billion in drinking water. We measured arsenic in drinking water samples from pretty much all of these homes. So the maximum contaminant level, this is the EPA limit for arsenic in drinking water, is 10 micrograms per liter. And this is the median 90th percentile of what we saw in drinking water. So we didn't even have a single drinking water sample that exceeded the maximum, even half the maximum contaminant level for arsenic. So it doesn't seem like the exposure is really out there in this population of people that had lung cancer and their matched controls. So I want you to keep that in mind. what the actual sample is. Although, you know, a lot of these samples are from municipal drinking water systems, so that would reflect the general population as well. So, but what we do see is there's actually moderate evidence of moderate deficiencies in certain nutritionally important trace elements. So chromium. So chromium comes in a couple forms, chromium 3 and chromium 6. Chromium 6 is the one that's associated with cancer, but low levels of chromium 3 are actually an essential nutrient. So there was a study by Goulart et al. Where they showed that myocardial infarction cases had lower levels of chromium in their toenails compared to individuals that were match controls in the case control study. So our study has less chromium than that study. Although the levels are kind of vary between studies at the thresholds you see. And being a male, a case, or a smoker was associated with lower chromium levels, which was interesting. So chromium is an insulin cofactor. And so in addition to this chromium, this myocardial infarction connection, Kentucky has basically twice the national rate of type 2 diabetes. So basically what happens is that chromium binds to this peptide that binds to the insulin receptor and makes it more responsive to insulin. So people with lower levels of chromium or chromium deficiency can show signs of insulin resistance. So I think this is something to look into further. That could be, especially because the chromium seemed to be quite a bit of a difference between the cases and controls. Okay, so I'm going to finish up this study of lung cancer, and I'm going to talk about a site that is actually contaminated. So while we're not seeing like widespread contamination of arsenic, you know, across broad swaths of eastern Kentucky, there are definitely places that have significant levels of contamination, like in a point source basis. So this was in Montgomery County. It's a neighborhood called Long Lane, and there used to be a wood treatment plant there that closed down, and it was kind of forgotten about, and they built a neighborhood there. So this is soil on the site, and you can see these green spots. So if you pick up some soil from one of those green spots and analyze it, you'll find that that soil is about 3% arsenic and about 7.5% copper. So these are extremely high levels, and of course, with soil contamination, it's always extremely heterogeneous. I didn't mention this before, but with trace element levels and organisms, we always do this log normally distributed. So you'll have a whole bunch of low-level exposures and then just a few that are really high. And part of it is this heterogeneity in the environment. So that, you know, there was a lawsuit and everything, and it had to be cleaned up. They had removed the soil. So we wanted to. I was working with Wayne Sanderson, who has got involved with the health department of Montgomery County to sort of monitor the cleanup of the site and his students. And one of the things that came up was when you have contaminated soil versus like drinking water or more diffuse exposure, wouldn't the toenails be subject to external contamination? And that would throw off the measurements. So we actually did some experiments. This is Wan Jin Kim. She was an undergraduate student in my lab this summer. She was with the summer undergraduate research program in environmental sciences. And we set up this way of taking the soil from the site and using toenails from volunteers, and we made a device that sort of simulated the toenails being drugged through the soil like thousands of times. We got them good and contaminated. We have a procedure for removing external contamination because we have to remove nail polish and all sorts of other weird stuff. So if you look at these, so aluminum is a good marker for soil because of aluminum silicate minerals, things like that. This is the control levels. If we dirtied the nails up and didn't clean them, these are the concentrations. When we clean them, significantly different, but we remove about 98% of the aluminum on there. For copper, we are able to completely restore it to a controlled condition. So what we did was with these nails from the volunteers, we took each individual nail and cut it into 3 pieces and put it into one of these 2. So these are all completely matched. Iron, same deal. Arsenic, significantly higher than control, but just because we had pretty good power. We had like an N of 40 or something like that. But still we're removing like 98 to 99% contamination. So that means that we can use these samples as a marker of exposure. So if you look at the results, and this is from Wayne Sanderson's master's student, here it is, Mark, she did this as her capstone project. What I want to highlight is the concentration. So we're looking at toenail concentrations of arsenic and divided into categories. So we have less than 0.2, 0.2 to 1, greater than 1. You can see that the biggest difference that we saw in terms of statistically significant differences in the division among these categories is individuals less than 18 years old versus greater than 18 years old. We did see some differences between Hispanic and non-Hispanic, but that may have been because it was collinear with age, so it's not completely teased out. But this is the major thing here. But what you do see is that the levels did go down once the soil started to be cleaned up over the course of a year. So why do children have higher levels of exposure? So I'm transitioning to a different part of the talk that's going to be focusing mainly on children's exposure. And this is really relevant to us as soil scientists. So I talked about those patterns of activity and what people do and how long they spend doing it. Well, it turns out the EPA has this document called the Exposure Factors Handbook, where they put in an enormous amount of effort to studying like how long people take a shower, how much juice they drink, how long they brush their teeth, how much water they drink, you know, how long they do. They really try to study people's complete patterns of activity. So this one is for playing on dirt, which is kind of infuriating. I shouldn't say soil there. Playing on sand and gravel and playing on grass. Minutes per day. And you can see it's really children that spend the most time doing these activities. It's kind of a no-brainer, right? But it's all quantified here with actual data. And as a result of this, when you look at the average ingestion of dust and soil, so we're talking about a mixture of these things are separated, really it's around 1 to 2 years of age where you see the peak level of ingestion of soil. So the average child in this age group consumes or ingests about 90 milligrams of soil per day. The upper percentile is a couple hundred milligrams. But then you have soil pica, which is children that are eating soil on purpose. That can be up to a gram a day or so. So this is the reason why children tend to be more highly exposed to things that are in the soil, and they tend to be sort of the what we call like the most sensitive receptor in terms of exposure. So I'm going to talk a little bit about lead exposure now, transitioning to some different contaminants here. Because of that soil and dust ingestion, and because of certain things that are specific to children's physiology, they're very susceptible to lead toxicity and exposure. So children have more efficient gastrointestinal absorption of lead. Their brain is developing. Lead is a neurotoxicant. Their bones are being remodeled. So lead can substitute for calcium in bone. And as the bones are remodeled, it can be liberated. And as I mentioned, higher ingestion levels of soil and dirt, or soil and dust. So this is a graph showing the total use of lead in paint and gasoline, the function of year, and then the total combined. So this year, 1976, peak lead usage was the year that I was born. So that probably explains a thing or two. In fact, if you look at the lead levels in children's blood during that time versus now, you would predict at least like 6 to 10, IQ points difference. So for this study, teamed up with Pat Ryan. He's an epidemiologist at Cincinnati Children's Hospital. So I mentioned that Cincinnati is sort of on the fringe of Appalachia, and a lot of the Appalachian diaspora lives in Cincinnati. Juliana Donser, she's a undergraduate student in the NRES program who also participated in research in my lab as part of the SURES program. She's actually the lead author on this paper, which is amazing. She writes very well and has done a very good job of getting ready to submit it. We had collaborators with the New York Department of Health, University of Albany, So what we were trying to look at was its toenail lead concentrations, the biomarker of surveillance of children's exposure to lead. So right now, the way that lead exposure is surveyed in children is primarily through blood analysis. But this requires a phlebotomist to take a blood sample from a child. We're talking about taking an invasive sample from a child, something that requires going to a health care facility, which makes it exponentially more expensive than using toenails, which could be self-collected and mailed in. So if we wanted to survey children's exposure, it would be much easier if their parents could take toenail clippings and send them in. So we needed to evaluate this because blood lead is sort of the gold standard for exposure. So we sort of jumped on to the Cincinnati Children's Asthma and Air Pollution Study cohort. So this is a cohort of children that have been followed, I don't know if it was since birth, but shortly after birth, and they're 12 years old now. We were able to get samples from when they're 12 years old to analyze. And they actually go to a healthcare facility to collect these samples. There were 252 children involved in this study, so toenail and blood samples. Also, the children and their primary caregiver gave an IQ test, because that's the main effect of lead exposure, is an effect on cognitive function. So these are just sort of the summary statistics. You can look at the breakdown, male, female, race, age. And when we look at the blood lead, so BPD is blood lead and TPD is toenail lead. We look at the mean concentrations, they're not too high. So the 0.57 there, that's actually pretty much background levels of lead. I think the current sort of World Health Organization guidelines is around 5 micrograms per deciliter. Not super high. But what you'll see is no level of lead really doesn't have an effect. And you can look at, these are the IQ scores. The caregivers are somehow have a couple points higher than their children. Body mass index, etc. So this is the relationship between toenail lead and blood lead. And what you can see is pretty much a scatter shot. Not a really, I mean, it's a highly significant relationship. This is the slope, but the R-square is only 0.24. So it's not like real predictive, but it follows the same basic trend. So part of that could be that there's a time lag between the toenail values and the blood values. So the toenail clippings that we took reflected exposure from a year before when the blood samples were collected. So we're going to try to follow this up with some longitudinal measurements where, we analyze blood from the year before the toenails are collected. Also, the low overall concentration means that you're not going to get a really high R-square value just because of the range and actual values that we had. If you had children that were exposed to much higher levels, we'd probably have a higher R-square value just by the nature of the statistics. So these figures up at the top are just unadjusted regressions of log toenail lead and log blood lead versus IQ score. And you can see that there's a significant relationship for each one of those. Interestingly, for the blood lead, so the log value of about 0.125, which is a very low blood lead level, much lower than the current guidelines. There wasn't a single child with an IQ over 100. So, and that's pretty much only slightly above background levels of lead. But of course, you can't look just at that because it needs to be adjusted for several things. So we adjusted for caregiver IQ, community deprivation index, which sort of takes into account socioeconomic factors, and body mass index because it was significant in our multiple regression model. So these are the adjusted betas. So these are the decrease in IQ per unit increase in lead. You can see that the relationships are different. So it's not, the toenails aren't like exactly predicting the blood lead like in a very quantitative way. However, they could be used as rapid surveillance just to get sort of an idea whether there's a problem in a given area and then go and follow up with the blood levels, which is what you would need to really relate that to the effects. So I think it needs a little bit more study, but it could be a useful tool. So for situations like in Flint, where you have like an enormous city where all of a sudden we're worried about lead exposure in children all over the city, how expensive would it be to get children from all over the city to, you know, for an initial screen to see where the most problematic areas are. So it could be useful. Okay, so the last thing I'm going to talk about doesn't have any results yet, but it's something that we're just starting. So I'm part of this center that was just funded by NIH. It's an NIH P30. Dr. Shi is the PI on that, and a lot of people were involved, called the Center for Appalachian Research and Environmental Sciences. So this is a NIH funded center. And I was awarded a pilot grant along with a number of other individuals listed here to look at water quality issues in a community engaged study in Martin County, Kentucky. So this is a picture of water that comes out of the tap in Martin County, Kentucky, if there's water to actually come out of the tap. I mean, it doesn't always look like that, but in certain places in the water grid, it can look like that. This is their drinking water treatment plant. It was built to service, you know, a few hundred people, and it's servicing like 10,000 people or something like that. The water lines are pretty severely dilapidated, so they lose up to 70% of the water that they pump into their water grid. So the way that I got involved with this was through Ellen Hahn. She's a professor in the College of Nursing that works a lot with community engagement and health issues. She's the leader of the community engagement core of the CAC of the study. And we have a sort of like a external advisory board of people from the Appalachian region of Kentucky that are interested in health issues. So they identified this as a concern for the region. So Ellen got a bunch of people into a room and said, does anybody want to take this on? And nobody raised their hand, and they all looked at me, so I got involved. But I'm really glad that I did, because it's been really rewarding to be involved in. So Wayne Sanderson and I went out and had like a community meeting with people in Inez, Kentucky, which is the county seat of Martin County, and listened to what their concerns were, and started working on developing a pilot proposal. We submitted that, got it funded. And then Alan and the CAC organized these key informant interviews to help us develop our study even further. So these are just sort of some statistics. So pretty much every quarter, Martin County is in violation of drinking water quality standards. So this is like from during 12 years, they haven't had an average of like 10 boil water advisories per year. You know, sometimes there just isn't water. I've experienced this before. I worked for the Geologic Survey in Puerto Rico, and they have water issues there because landslides fill in the reservoirs and they can't catch enough water. So you come home from a hard day at work, sweaty, you get home, you turn on the tap, there's no water, take a shower. It's a really horrible thing. This is happening, you know, right here in Kentucky. So the problems go way back. So this was in October 2000. This is the drinking water intake on the Tug Fork, which is a tributary to the Big Sandy. Back in October 2000 was like the biggest coal slurry spill ever, I think. 1.2 billion liters of coal slurry were spilled and completely buried the water intake. So this is them cleaning it up. It's hard to see this here, but this creek was like completely filled with coal slurry and it just killed everything. Pretty bad stuff. So their issues go way back. It's nothing recent. You know, sometimes the water comes out looking like this, and people don't really drink the water there, and they're like really even afraid to bathe in the water. People cook with bottled water. They have to drive like 30 miles to the nearest Walmart to get large quantities of bottled water. So a lot of people resort to getting water from places like this, just springs, or they may just take a pipe and stick it in the side of a hill where there's a spring, or they may catch water in their swimming pool and use that for washing and cooking. So it's a pretty bad situation. You really don't know what's in the spring water. This hasn't been evaluated at all, but it's still, you know, probably better than what's coming out of the tap. So this is the drinking water system. One of the problems here is that this is an extremely hilly terrain, so the pipes have to go up and over these hills and down into the hollows, and if you don't have proper valves regulating the pressure, when the pipes get brittle, they break, and that's the cause of a lot of the leakage. So our sampling design is going to look at distance from the treatment plant here in Inez through the drinking water grid. So this is Jay Christian. Epidemiology is doing the spatial analysis. And we're going to randomly sample from these different segments of different branches, different distances from the drinking water plant. And these different branches were constructed at different times using different materials and things like that. So one of the problems is that they have a lot of disinfection byproduct formation. So when you have natural organic matter in the water and react it with chlorine, you get haloacetic acids and trihalomethanes. And this is what they consistently are in exceedance of drinking water quality standards for month after month. So this is going to be one of our main focuses. And part of the reason that they have it is that they have an inability to flush the pipes out. When you can't flush the pipes out, biofilm and sediment accumulates in the pipe, which means you have to have more chlorine so that you have enough residual, like free chlorine when it comes out of the tap to make sure there's no bacteria in there, which causes more formation of disinfection byproducts. Also, there's contaminants. When the lines aren't under pressure, then contaminants that are in the soil can infiltrate into the drinking water lines. So that creates problems, and you have to add more chlorine and just exacerbates the problem. So, and this is something that isn't part of the pilot, but this is sort of a tie into agriculture that I've been thinking about, because one of the engineers told me that the amount of algae in the reservoir seemed to be correlated with the level of disinfection byproducts. So does land management practices have an influence on them? So, if we're allowing more nutrient runoff into surface water, that's going into the reservoir, causing eutrophication, causing algal blooms, so you have increased particulate organic carbon, which causes more disinfection byproduct formation, and then the person that is managing that land drinks that water. So it's sort of like a boomerang effect. So this is something that I'd like to develop. Anybody that's interested in collaborating on something like that should talk to me. So one of the main effects that we're concerned about with disinfection byproducts is kidney cancer. So this is what your kidney should look like, and this is what it looks like when you have stage 4 kidney cancer. It's pretty horrible. And it turns out that Martin County has one of the highest rates of kidney cancer in the state. They also have these disinfection byproducts. We're not going to be able to correlate with a pilot study levels of disinfection byproducts with kidney cancer, because when you have cancer as a low incidence disease, you need a really large sample size. So we'd have to sample like 10% of all the people that live in the entire county probably to get a statistically significant result. But this is pilot data, so we're hoping for a larger study over the whole region, because this is by no means an isolated problem. So with the disinfection byproducts, it's estimated that about 15 million people in the United States are drinking water that exceeds the limits for DVPs. So the key informant interviews, Ellen actually placed an ad in the paper and got some people to come in and give interviews, and we use this to help develop our questionnaire. With a lot of people not drinking the water, we're also looking at what happens when you bathe in it. People are complaining about getting rashes and chemical burns and things like that. You feel sticky after shower. So we took all the feedback that we could get from the community and incorporated it into our survey to make sure that we're addressing the things that they cared about. So we're going to do these home visits, do health effects questionnaires, drinking water study. We're going to measure all the chemistry, do some spatial analysis, et cetera, et cetera. We're not going to find some like scientifically groundbreaking results here. We already kind of know how to solve this problem. But part of it is just getting local citizens engaged with us and doing science. So Ellen hooked me up with some people to collaborate with in the community out there. So there's a group called Martin County Concerned Citizens that works with drinking water issues. Mary Cromer, she's with the Appalachian Citizens Law Center. Ricky Draper, she's an Appalachian Transition Fellow. So this place called the Highlander Center has these fellowships to sort of train the next generation of leaders in Appalachia, and she's involved with Ricky. And Nina McCoy, she's the newest employee for the Plant and Soil Science Department. She's a retired biology teacher, so she's going to be in charge of field operations. And we actually set up, Wayne and his student Courtney and I, last week, we set up a lab at the Martin County Extension Office to measure total coliform and E. coli using this collar system. So they have like a room where they do these PE trainings, and they gave us a little space in there.
The microphone's back down,
Oh, whoops.
sorry.
This thing just doesn't want to stay on. So just more pictures. This is an attorney trying to learn how to pipette in my lab. That was kind of funny. So with that, I'm going to conclude. The person that I want to thank the most is Christy Shrestha. So she came when we started the lung cancer study, and she's been funded off of soft money, like pieced together through all these projects ever since. She's analyzed tons and tons of samples. When I hired her, I was like, "Are you sure you're okay with analyzing toenails and urine, blood every day?" And she's like, "Sure, no problem." She's been really, you know, none of this would have been possible without her at all. I'd like to thank the study participants, particularly in the lung cancer study. A lot of people that volunteered for this are deceased now. Kentucky Home Place nurses, Gary Palmer for helping me, and Roger Mollett, he works at the Martin County Extension Office, for helping me get that space to set up our lab out there, funding sources. Thanks a lot for your attention.
Questions?
So this was blood levels of lead. Does that mean just an immediate exposure, 24 hour, 48, or is it
Yeah.
tissue or something?
So that's a situation because lead is stored in the bones, and then it's sort of re-released over time as the bones grow. That's a situation where lead probably reflects more of like a total body burden of lead, or maybe a cumulative exposure. So, you know, they're all different. Like arsenic urine is not the best biomarker. For lead, blood happens to be the best. For most of the elements, though, you know, blood or urine varies a lot with short-term exposure. Like for mercury, if I just eat a meal that has a lot of mercury, then my blood and urine levels are going to go up for that 24 to 48 hour period. That was probably a bad example because mercury is pretty poorly eliminated, but for things that are eliminated very quickly, it was probably the worst example I could think of, actually. You're up here trying to think of stuff.
Is that lead exposure when you were young?
Yeah.
So I grew up in the area of Big Sandy region.
Yeah.
This is an issue pretty close to my heart, especially the water quality. Maybe a mile from where I grew up, there was a slurry pond that was filled in about the time this problem happened. And I'm just curious the impacts of filling those slurry ponds in with the groundwater contaminants. Does that water still reach the water system? Those contaminants still reach the water system?
I mean, they can. And so a lot of things that would be in there are analyzed for as part of regulatory compliance. One of the things that I'm trying to kind of get things together to look at is PAHs, which could be pretty abundant in coal slurry. So the PAHs that are analyzed for regulatory compliance are called pyrogenic PAHs, so they're made as part of a combustion product. The PAHs that you would find in coal or oil are a little bit different. They have extra methyl groups and things on them, and you wouldn't detect those in the analyses that EPA is doing on a routine basis. So we're trying to look at that, see if it might be something that could be missed. You know, I've also heard anecdotal stories from local residents that they threw all kinds of things in the slurry ponds, not just coal slurry, like whole tractors, you know. So you just don't really know what was in there sometimes.
I know of many pieces of equipment that's sunk in those slurry ponds.
Yeah, I mean, sometimes it may have been on accident.
So I am actually from Martin County.
Yeah.
So this is an issue very near and dear to my heart, and I was just wondering because I'm kind of trying to compile my own information to you know, because I'm actually a graphic designer and I'm making like pieces to advocate for Martin County. And so, just so I have my own little database of information, like since the slurry spill in 2000, are there like certain like elements or chemicals that are still prevalent in the water that we know of, like that are still left over from that at all?
I don't think we really know. Yeah, the only thing that I've had a chance to look at so far is the metals, and I don't see a whole lot. Because a lot of that stuff was dug up and disposed of, but I'm sure there's still things in the sediments, like in the tug port and things like that. But I don't personally know of any information out there about that. So, yeah. Yeah.
So do you let your kids play on the soil, Jason?
Yeah.
Yeah. You know, it's thinking about the connections there. I mean, I think kids probably play less on the soil than they used to, right?
Yeah, so it's even worse.
Who knows, or even better. I mean, if you think of the connection, you know, we're pretty disconnected from the environment these days, and kids are on their phone and on all this other stuff. And so maybe in the long term, it'll help their IQ if they're not looking at and other things. But I guess the lead exposure might have been from environmental paints and things, or do you think that's also still sort of soil geophaging thing?
Yeah, I mean, so that study was actually looking at air quality. So whether there was like particulate inhalation exposure. When you inhale particles, your lungs move a lot of those particles in the mucus out, and you end up ingesting it, like in the stomach. So Pat Ryan was looking at that sort of thing, so that could be one source. I mean, overall, the lead exposure levels to paint, I think, were the most significant. And so when lead paint stopped being used, they went down the fastest. And then when leaded gasoline stopped being used, it went down a little bit slower. But certainly children's lead levels are much lower now than they used to be, like an order of magnitude lower.
That's good.
Yeah. But they keep dropping. Now basically people say there's no level of lead that doesn't cause an effect. And you can sort of see that in the data I showed. Those were really low levels, and they were significant. I mean, the R square is only like 0.15, but still, you know, that's 15% of your IQ.
Yeah.
So.
Any other? Maybe one more, Todd.
So when you compared the toenail lead and the blood lead, did the substrate affect your analysis? I mean, was your repeatability the same in both the toenails and the lead?
Yeah, so
repeatability?
we use standard reference materials to make sure it's accurate, things like that. With the toenail lead, we basically digest all the toenails, so there's no repeatability thing there. It's like all one sample. And then if we take that digestate and then analyze it several times, you know, it would be similar to the blood. We're using the same like end technique to analyze it. It's just a different sample prep. So it shouldn't be that much different. We use a human hair standard reference material for the toenails. And so we know like what the variability between repeat measurements of that is.
Where does the standard hair come?
Japan.
Oh. You have one person sitting in a room exposing them to a certain.
No, what they would have done is like gone out to barber shops and collected like hundreds of pounds of hair and then like homogenize it and send it out to like 10 labs to analyze it. So you get like a consensus value.
Okay.
So, for the blood, we use goat. It's goat blood. They do some to get their blood.
All right, let's tell Jason, thank you for a very interesting.